circuit 2, and we are going to start the course after the midterms. Before midterms we have studied variable frequency circuits, and for that we have tried to find the transfer functions and also studied about the Bode plots. Now we are moving on towards the resonance and the resonant circuits. By definition, resonance is a phenomenon at which the response of the circuit is maximized, and by response we mean that it can be a current, it can be a voltage. If I have to explain this statement by a simple RLC circuit, resistor, capacitor and inductor, the current is passing through these series elements, the current is same through all the elements, the voltage across the impedance is V, and this voltage is just divided among all the elements R, C and L. Now if I had to maximize this current with the changing frequency, there will be a certain frequency at which the I will become I maximum, and that frequency is known as resonant frequency, and that particular instant at which the I becomes I maximum, the system is said to be in resonance. This phenomena is used in many applications, and there are different types of filters that we design. So very common used filters are noise cancellation filters, then there are band pass and reject filters, then there is a low pass filter and a high pass filters. The tuning circuits that are used in radios and television to change the channels, we are working on the phenomena of resonance. Basically there are two types of resonance circuits, series resonance circuit, and then there is a parallel resonance circuit. So I'm going to start with the series resonance circuit. It is actually the series combination of elements R, C and L. Again, the current that is passing through the series elements is the same through all the elements, but the voltage is being divided among all these three different elements. So now if I have to calculate the equivalent impedance of the circuit, Zj omega, that will be R plus j omega L, which is the inductive reactance, XL, plus 1 over j omega C, that is the capacitive reactance, XC. So the impedance will be R plus j omega L minus 1 over omega C. Now in this case what we want to maximize the current across the impedance, and the current will be maximized when the impedance is minimized. So we know the basic formula for the current from the Ohm's law, I is equal to V over Z. So if Z is minimized, current will be maximized. So to maximize the current we have to minimize the impedance, and by changing the frequency we can just make the imaginary part of the impedance equal to 0. Then the impedance becomes totally resistive and the current will be maximized. So what we have to do, I have to just make omega L minus 1 over omega C is equal to 0, and from that after solving this equation I can get omega naught. So this frequency at which omega L minus 1 over omega C is equal to 0 is known as resonant frequency, and if we are at resonant frequency, impedance is minimum, so the current will be maximum. So what we have done, we have maximized the response of the circuit, so the system is in resonance at the resonant frequency. Now if I have to define the characteristics, basic characteristics of the series resonance circuit, at resonance it will act as a resistive circuit. And what are the properties of resistive circuit? The voltage and current are in phase. So if they are in phase, the angle between voltage and current is 0. So if the angle is 0, the power factor is unity, because power factor is just the cosine of the angle theta z. So this is the first property. The second property is the impedance is minimum, so the current will be maximum. Now if I have to move towards the frequency response of the series circuit, what I have done, I have drawn the impedance value for different frequencies. Like this is the impedance magnitude, and I am changing the value of omega, the frequency. So there is a curve that I got, and at omega naught we know that the impedance is resistive. Only a resistive part is available or present in the impedance value. So at omega naught we are getting R. Now there are two different cases. One is for the frequency values less than omega naught, the other one is for the frequency values greater than omega naught. Well, omega is less than omega naught, so omega is a smaller value. If I had to find the inductive reactance, that will be 1 omega L, right? So if omega is a smaller value, XL will be a smaller value. Similarly for XC, it is 1 over omega C. This is capacitive reactance. If omega is a smaller value, XC will be a larger value. So from here we can deduce that for omega less than omega naught, the impedance is dominated by capacitive reactance, and after that omega is greater than omega naught. For this particular case, XL is equal to omega L. So if omega is a larger value, XL will be a larger value, but in case of XC, 1 over omega C, omega is a larger value, XC will be a very small value. So for the frequency values greater than omega naught, inductive reactance will be a dominant part of the impedance. Now, if I have to draw the curve for the current through the circuit for different values of frequencies, again we will have the maximum current when we have the minimum impedance, which is omega naught. So at omega naught we are getting the maximum current, and before and after omega naught the current is reducing because the capacitive reactance and inductive reactance are increasing respectively. From this particular graph, the impedance graph, we can again define three different cases. The first case is omega is less than omega naught, XL will be a smaller value and XC will be a larger value. So it shows that if the inductive reactance is small, the voltage across the inductor will be small, and if the capacitive reactance is a large value, the voltage across the capacitor will be a large value. Now if I have to draw the phasor diagram, I am taking I on x-axis, and then I am just drawing different phases for the voltages across resistor, capacitor and inductor. For the resistive voltage, it is in phase with the current, theta g is equal to 0. For the inductive voltage, it is 90 degree out of phase, but the voltage VL is leading the current, because we know that in inductors voltage leads the current. Now for the capacitor, the capacitor voltage is lagging the current by 90 degree. So I will just write it down. Capacitors current leads the voltage. Now if I have to find the resultant vector for the voltage across the impedance, that will be the addition of all the voltage phases. So this is VR, and if I will add VL and VC, so this whole vector is VC and this is VL, so the addition of these two vectors will be VC minus VL. So if I use head to tail rule, I got V1, which is lagging the current I. Now if I have to move towards the second case, omega is equal to omega naught, resistive circuit, so the VL and VC, they are equal. So if VL and VC are equal, it means they will cancel out each other, and the voltage across the whole impedance will be the same as the voltage across the resistor. So the V1 and I, they are in phase, theta g is equal to 0, so the power factor will be unity. In the last case, omega is greater than omega naught, again XL will be greater than XC. So if XL is greater than XC, the voltage across the inductor will be greater than voltage across the capacitor. If I have to draw the phases, again the VR is in phase with current, the VL and VC are 90 degrees out of phase, but the value of voltage across inductor is greater than the voltage across the capacitor. So if we add VL and VC, that will be this particular phasor will be VL minus VC. So I am again adding all the phases of the voltage, I get V1, which is leading the current I. So in inductive case, we have voltage that is leading the current of the network. So till this point we have covered three different cases for omega is equal to omega naught, omega less than omega naught and omega greater than omega naught. Now we also know that at resonance the voltages across inductor and capacitor are equal. Now if I have to use the inductor, the voltage VL is equal to omega naught L. This omega naught L is, this is XL, and this is the current. And we are calculating this voltage at resonance, and at resonance the impedance is equal to resistance, right? So if I have to calculate the current through the circuit at resonance, that will just be the source voltage, whatever the voltage is across the whole impedance, divided by the resistor, because XL is equal to XC, they will cancel out, so we only have a resistive element in the impedance. So putting this equation, I is equal to Vs over R in the above equation, so we get VL is equal to omega naught L into Vs over R, and VL is equal to omega naught L over R into Vs. So now if we have to find the voltage across the capacitor, again the formula will be the same. Vc is equal to I, the current through the circuit, into the capacitive reactance. Now capacitive reactance is equal to 1 over omega naught C, and the current that we already know across the circuit will be Vs over R. So we'll put these two values into the first equation, which is equal to Ix. So we get voltage across the capacitor is equal to the source voltage divided by omega naught RC. So from equation A and B, we get that omega naught L over R is equal to 1 over omega naught RC. So we define a new term that is known as quality factor. Now actually quality factor, it just defines the sharpness of the gain curve. So here it is using the admittance magnitude, but it can be current or it can also be a voltage gain. So it actually just defines the sharpness of the gain curve. Sharpness will increase with the increase of quality factor. So if the Q value increases, the sharpness will increase. So if I have to define the different Qs in these curves, there are three different curves. So Q1 is greater than Q is greater than Q2, because the sharpest one is Q1, so it is the biggest value, and the least sharpness is in Q2. So the last one, that is the most flat curve, it is Q2. So the Q2 is the smallest value and Q1 is the largest value. So the second term that we have to define for the filters and for the resonant circuits is the bandwidth. And if I have to define the bandwidth, these are actually the range of frequency values that are bounded by two half power frequencies. So one frequency is less than omega naught is the resonant frequency, and the other frequency is higher than omega naught, which is WHI. So the range of the frequency for which the minimum power value is greater than the half of the maximum power is known as bandwidth. So all the signal values or the gain values for these frequency values, these are greater than the half of the maximum power. And we know that at this point, at omega naught, P is maximum. So bandwidth is actually the range of frequencies for which the minimum power is at least half of the maximum power. Now for the values of the y-axis, these are actually the gain values. So it can be a voltage gain or the current gain. Now if I have to find the half power values for voltage and current, half power values for voltage and current, we already know that power is actually proportional to the square of the magnitude of either of the gains, voltage or current. Voltage or current. We know that the maximum power is equal to I square max R. So maximum power occurs when we have the maximum current, and this is actually occurring at omega naught, right? So if I have to reduce the power to the half of the previous value, so we have to divide that power with 2. So if I am dividing by 2 and I have to calculate the new I for the half power, that will be I max over under root 2. So what I have done, I have taken this 2 inside the square. So that is under root 2. So the new current value will be I max over under root 2. Similarly, if I have to calculate the power, half power, using the voltage value or voltage equation for the power, that will be P max is equal to V square max over R. If again I have to calculate the half power, I have to divide the formula by 2, and by calculating it or bringing 2 inside the square, it will become under root 2, and the new value of voltage for which the power will be half of the maximum will be V max over under root 2. So that's why I say that the value of the gain V or I will be 1 over under root 2 times the maximum value when the power is half, right? And this 1 over under root value is because power is proportional to the square of the magnitude of either gains V or I. So till this point we have covered very basic concepts of the series resonant circuit, and now we are going to apply that. We have a series RLC circuit, and we have a resistor of 2 ohm, then we have a capacitor of 10 microfarad and an inductor of 25 millihenry. We have a voltage source of value 10 angle 0, and there is a current that is flowing through that. Now we have to find the voltage across all the elements. The elements are resistor, inductor and capacitor at resonance, right? So at resonance the voltage across capacitor and inductor, these are equal. Then we have to find the resonant frequency, and we also have to find the quality factor. Resonant frequency, that is equal to omega naught. Formula for omega naught, that is equal to 1 over under root L and C. So if I use the values that are 25 millihenry and 10 microfarad, so that will be 10 into 10 raised to minus 6 into 25 into 10 raised to minus 3. So you will get the value for omega naught, that is 2000 radian per second. For quality factor, we know that Q is equal to omega naught L over R. It's also equal to 1 over omega naught CR. So whatever formula you want to use will give you the same answer. I will be using this one. So Q is equal to omega naught L over R. So it will be 2 into 10 raised to power 3 into 25 into 10 raised to minus 3. And divided by the value of resistance, that is 2 ohm. So now after calculating we get the value for the quality factor equal to 25. We also have to find the voltages across all the elements, right? So we will start from resistor. Now for the voltage across the resistor, we know that VR is equal to IR, but we don't know the value of current, right? But we know that at resonance the impedance is equal to resistance, right? So I is equal to Vs over C is equal to Vs over R. The value of Vs is 10 angle 0. The resistance is 2. So the value of current is 5 angle 0 ampere. If I put this value in VR, so VR will be 5 angle 0 into 2 is equal to 10 volts. Now for the inductor voltage, PL is equal to J omega naught L I, and this is equal to 2000 into 25 into 10 raised to minus 3. So inductance is 25 millihenry, omega naught is equal to 2000 radian per second, and current is 5 angle 0 ampere. So from here we can calculate the VL, and the value will be 250 angle 90 degree. Similarly for the capacitor voltage, we have VC, and VC is equal to I over J omega C. So it will be again 5 angle 0 over 1 angle 90 into 2000 into 10 microfarad. So this will give you VC, which will be equal to 250 angle minus 90 volts. So This was a simple example to how to solve a simple RLC circuit at resonant frequency. Now for the second example, what we have to solve, again we are given with a RLC series resonant circuit. We have a source of 30 cos omega t voltage, and then there is a current IT that we have to find. There is an inductor L, and whose inductance that we have to find. There is a resistor of 5 ohm, and then there is a capacitor of 100 microfarad. We are given with the resonant frequency that is equal to 10,000 radian per second, and we have to calculate the inductance value as well as currents at omega naught and omega naught by 3. Starting from the value of inductance, we know that omega naught is equal to 1 over under root LC, and from here I can say that L is equal to 1 over omega naught square into C. So that will be, what is the value for omega naught? That is 10,000 square into 100 microfarad. So the value of inductance will be 0.1 millihenry. So that was the first part where we have to calculate the inductance value. Now for the values of current and current values. So first we have to find the current I at omega naught. We know that at omega naught impedance is equal to R, so I is equal to Vs over Z is equal to Vs over R. Now from the circuit diagram we know that the source voltage is 30 angle 0 volt, right? So here we can write it down as 30 angle 0 divided by the resistance, that is 5 ohm. So that will give you the 6 angle 0 ampere. So that was your current at omega naught. Now for the current value at omega naught by 3, first we have to calculate the impedance. Because at resonance we have impedance equal to resistance, but any other value that is greater than or less than omega naught, the impedance will be combination of capacitive and inductive reactance plus the resistive value. So impedance is actually at omega naught by 3, impedance is equal to R plus J XL minus XC. So calculating XL, that will be omega L. What is omega? It is 10k by 3 into 0.1 millihenry, right? So this is your omega naught, and where we have to find, this is omega naught by 3. So omega is equal to omega naught by 3. So XL value is 0.33 ohm. Similarly, we can calculate XC, that is equal to 1 over omega C, and we get the value of 1 over 10k divided by 3 into 100 microfarad, and XC will be 3 ohm. Now the impedance will be R plus J XL minus XC, and I is equal to Vs over R plus J XL minus XC. Vs is equal to 30 angle 0 divided by 5 plus 0.33 minus 3 J. Current at omega naught by 3 is equal to 5.294 angle minus 28.7. So the maximum current will be obtained at the resonant frequency, that was 6 ampere. Any value other than the resonant frequency will give you the current value that is lesser than the maximum value. So this was the first lecture on series resonant circuit. See you next time.